Hey, have you ever stood on a big bridge and felt that little shudder as a truck rolls by? We think of these things as totally solid, right? Symbols of strength. But what if I told you that a simple, steady breeze, not a storm, just a breeze, could make one of these massive structures twist itself into pieces? Let's get into how that's even possible. It's a pretty wild image to get your head around, isn't it? A steel bridge just twisting like it's made of paper. But this isn't some sci-fi movie plot. It has actually happened. And the force that did it is way more subtle and honestly way more fascinating than just a big storm. See, the answer doesn't have anything to do with how much brute force you can hit a bridge with. It's not an earthquake, it's not a bomb. The real secret, the key to this whole mystery, is a hidden rhythm. It's a pulse that's already inside the bridge, just waiting. And when an outside force happens to match that exact same rhythm, well, that's when things get really dangerous. So, how in the world does this actually happen? To figure it out, we've got to dive into the startling physics of vibration. You know, it might look like the bridge is possessed, but the explanation is pure, unadulterated science. And here it is. This is the classic, absolutely terrifying example. The Tacoma Narrows Bridge. They called it Galloping Gertie. It famously collapsed just a few months after it opened. And what was the culprit? Not a hurricane, not some massive storm. It was a steady, pretty boring 40-mile-per-hour wind. This one event basically forced engineers to throw out their old rulebooks and completely rethink how they understood the forces of nature. Okay, so let's get this perfectly clear because it's the most important part. We are not talking about a single giant hit. That's brute force. Think of trying to knock down a brick wall with one giant sledgehammer swing. What we are talking about is a rhythmic force, a whole bunch of small, perfectly timed pushes that add up, testing the structure's stability in a totally different and kind of snaky way. All right, so if the bad guy here is a rhythmic force, our first job as detectives is to find the bridge's weak spot. We're on the hunt for our first big clue, what I like to call the secret hum. And that secret hum, it has a proper scientific name, natural frequency. It's the unique speed that literally any object, from a guitar string to a skyscraper to our bridge, will vibrate at if you just tap it and let it go. You can think of it like an object's unique musical note or its acoustic fingerprint. And this idea applies to everything. I mean, everything. A giant skyscraper, it's actually designed to sway, but very, very slowly. That's a low natural frequency. But a delicate wine glass, you know that sound it makes when you run your finger around the rim? That's its high natural frequency. Everything has its own rhythm. So right there, that hum, that natural frequency, that is the bridge's precise point of vulnerability. It's the secret code. And if an outside force can figure out that code and match it, it can unlock some absolutely catastrophic movement. So if the bridge's natural frequency is the vulnerability, what's the weapon that targets it? We need to find the accomplice in this case, the thing that delivers that perfect rhythmic push. And that accomplice is a phenomenon called resonance. And folks, this is the big one. This is the whole ballgame. Resonance is what happens when the rhythm of an outside force, like the wind, perfectly, and I mean perfectly, syncs up with the natural frequency of an object, like our bridge. The energy from each little push just gets added to the last one, and the vibrations don't just add up, they multiply like crazy. The absolute best way to understand this is to think about pushing a kid on a swing. You don't just shove them whenever, right? No, you naturally find the rhythm of the swing. That's its natural frequency, and you time your little pushes to match that rhythm perfectly. Each one of those gentle pushes adds more and more energy, sending the swing higher and higher. That feeling right there is resonance in action. And that is the whole mind-bending takeaway here. It is not about how big the pushes are, it's all about the timing. With resonance, a series of tiny, almost unnoticeable forces can combine to create a massive, overwhelming, and as we've seen, a potentially destructive result. Okay, we've got our clues. We have the bridge's vulnerability, its natural frequency, and we have the accomplice, the physics of resonance. It is time to put it all together. This is the aha moment where we crack the case. So this is the final question, the one that brings it all home. We get the science now, but what was it in the real world? What actually provided that perfectly timed rhythmic push that brought down the Tacoma Narrows Bridge? And the answer is almost disappointingly simple. It was the wind. Not a hurricane, just a steady wind blowing at just the right speed. As the air flowed over and under the bridge deck, it created these little swirls of air, called vortices. And this pattern of swirling air created a perfect push-pull, up-down rhythm that just happened to be the exact same frequency as the bridge's natural hum. This table just lays it out perfectly. You've got the bridge with its built-in hum, its hidden vulnerability. Then you've got the wind, providing that perfect push at a perfectly matching frequency. And what's the outcome? Catastrophic resonance. The energy from the wind just kept pumping into the bridge, push after push, until the twisting motion became so extreme that the steel and concrete just couldn't take it anymore. And then it failed. Now, the collapse of the Tacoma Narrows was a total disaster, but it also became one of the most important lessons in the history of modern engineering. So how do we use this knowledge today? How do we engineer against this kind of chaos? Well, if you look back at those older designs, the flaws are kind of obvious now. They had these big, solid, flat sides that basically acted like giant sails, just catching the wind. They were also built to be super rigid, with no give, which ironically made them more brittle. And the biggest thing, engineers back then just weren't calculating for this hidden danger of resonance. It wasn't really on their radar. But today's bridges, oh, they are so much smarter. They have these huge damping systems. They're basically giant shock absorbers that take all that vibration energy and turn it into heat, so it just disappears. The decks are shaped aerodynamically, kind of like an airplane wing, so the wind flows smoothly around them instead of creating those rhythmic pushes. Some even have huge weights placed irregularly to break up any rhythm before it can even get started. So here's the bottom line. Instead of trying to fight nature with pure brute strength, modern engineering has learned how to outsmart it. The whole philosophy now is to design structures that are fundamentally out of tune with any rhythm that nature might throw at it, making sure resonance can never get a foothold. And that really gets to the core of it, doesn't it? This isn't just a cool story about a bridge falling down. It's about a much deeper understanding of the physics that governs our entire world, and about learning how to build things that can safely coexist with these powerful, invisible forces. It really makes you wonder, right? Our world is just filled with these invisible rhythms. It's why soldiers are told to break step when they march across a bridge, so their footsteps don't create a resonant frequency. It's why a concert hall sounds amazing. It's designed to control resonance perfectly. This story of the vibrating bridge is just a powerful reminder that sometimes the smallest, most consistent forces are the ones with the most power. Pretty cool stuff to think about.